Okay, I think it's working now. So, continuity. So first thing you always want to know, a polynomial is always continuous, and you can see that if you graph it. So let's say I have a polynomial of like degree 1, so that's like x equals to y. Everywhere you go on this graph, it's always going to be smooth. There's no breaks, there's no like jumps in between. So it's always going to be continuous. That's the basic definition of continuity if you look at a graph. Visually, it means there's one smooth, unbroken line or curve. And that's true for any polynomial. So if I have x squared, it's going to be smooth everywhere. If I have x cubed, it's going to be smooth everywhere. If I have, that is not an arrow. If I have x cubed plus 3, that's going to be smooth everywhere. So basically, any polynomial is always going to be continuous regardless of what degree it is. But remember, a polynomial is like x cubed plus 3x plus 2. A polynomial is not 2x over x cubed plus 1. That does not apply to this function over here. Okay, so then the second thing is types of discontinuities if you look at a graph. So our first type is going to be this thing called a jump discontinuity. So that means if I have like this and I go over here, and then I have one over here, there's like a jump. As you can see, there's a jump from this point to this point. So this is called a jump discontinuity. My second type is going to be a removable discontinuity. That's when I have, I have like a graph like this. So as you can see, it all goes to the same place, but at just one point, it's not continuous. So if I asked you if it was continuous at this point, x equals a, your answer would be no, because there's a discontinuity there. And your third type is going to be an asymptote. So if I have a graph that looks like this, over here at x equals to a, the function is not continuous because on the left side, it goes to infinity. On the right side, it goes to negative infinity, which means it's not continuous. Okay, what was the next thing I wanted to do? Do you remember?
We should talk about square root functions.
Oh yeah, I remember. Okay, so one thing I've noticed is a lot of confusion about like the difference between domain and continuity. So usually when you're talking about continuity of a function, you mean continuous in its domain. Like I'll say, is the function continuous, right? But if I have nothing else attached, what's usually like attached without actually saying it is in its domain. Or otherwise you'll have like intervals, right? They'll say you're continuous on x equals 3 or from the interval like 2 to 6. But if they don't have any of this stuff, that means continuous in its domain. So if I take the function root 1 minus x squared and I graph it, that's going to be a semicircle like this. And it is a continuous function because if you look, it's all smooth. There's no unbroken points. But on x equals negative 2, there is just no function. And that doesn't mean it's not continuous there. The function is just not in its domain. So you can't possibly do that. So you would still call this function continuous, even though it does not exist everywhere.
Yeah, so when you're looking at just the function itself, the reason it seems kind of confusing is because you're looking at, oh, x cannot, or like y cannot be these values, x cannot be these values, so it must break, it must not be continuous. No, it's just that it just doesn't exist there, and so you're only looking at the part where the function does exist.
Yeah. Okay, now, you guys have left-hand limit and right-hand limit, right?
Those are bitches.
No cussing. Okay, yeah. So those are actually like pretty easy. It's just that they can get like really easy to misinterpret. So let's say
when you have a graph. When you don't have a graph?
yeah. So let's start with graphs and then we'll move on from graphs to word problems. Sorry, I mean numbers without graphs. So if I have the function like okay, here, and I choose this is about what? 2? I choose 2 and I say this is f of x and I say is f of x continuous at x equals 2? And your answer is yes, because there's a smooth unbroken point. Now let's say I make a new function. I do and we'll call this g of x. And I ask, is g of x continuous at x equals 2? And your answer is no, because as you can see here, there is a removable discontinuity. There's actually a fourth type of discontinuity, but for your purposes, you won't need to know that, so you should
Really, you should just know that there's a discontinuity.
Yeah, but this is the types is like stuff you'll need to know in BC, but it's really useful to know them now, so that's why I'm going over them. So it's really easy to see this stuff when you have a graph, but I think when you're solving for it with like numbers, it's different. So in that, it's like your left hand limit and your right hand limit. Sorry, my handwriting is like terrible. They've got to match, or else the function is not continuous at that point. Or at that point, in this case, its limit notation is like lim as x goes to that point. So like x goes to whatever it is, x goes to a, right? But the thing I always see people like forgetting is that there's actually like, this is one condition, yes, but there's a condition even before that. So like this is condition 2, this is condition 1. F of a must exist. So a lot of the time, you'll see people who get functions with graphs that look like, I don't know, like this. And then this is the point A. And the problem says, as limit of x approaches A, let's call this f of x. X. Basically, is it continuous? Is this continuous? I don't know why I put the as there. And if you look, as it approaches from the left side, it approaches this point. As it approaches from the right side, it approaches this point. So, if you weren't checking, you'd say this is continuous. But the thing is, it doesn't exist at point A. So therefore, it's not continuous. And that's really easy to see with a graph, but it's really hard to see when you're just doing, like, number problems. So make sure you keep that in mind.
Show how to do it with a number problem.
Yeah, that's what I was gonna do, Ananya. I need
Like
to make
a
a number problem on the spot. What's a number problem?
F of a rational expression
Equals. Okay, it's working. It's working. Cool. So, sorry, we took a little break in between.
I didn't think you messed up.
No, I didn't. I didn't know.
Of the recording, and then went, oh wait.
No. I only messed up on the last 2 seconds, and it wasn't even like
The last 2 seconds.
last 2 minutes. Fine, but like it wasn't.
It was 7, at least 7.
No, it wasn't 7. It was only the but like okay. So where we left off, we were talking about right hand limits and left hand limits graphically, and then we were like we should do a number problem. So here's our number problem. Let's say f of x equals to x over x plus 1, right? So then where does the function not exist? Where the denominator is equal to 0, because you can't divide by 0. So x plus 1 equals 0, x equals negative 1. Pretty simple stuff so far. And since this is the point where it doesn't exist, this is where you're going to take your limit to. So I do limit as x approaches to negative 1. Is that a better arrow for you, Ananya?
No, that's even worse.
What's wrong with my arrows? I don't understand.
It's not an arrow. It literally looks like...
Do you want like this?
Looks like a backwards member sign. Like member of set. It looks like a backwards.
You don't deserve speaking rights. Okay, anyways. And you can split this, since we're doing left hand limit and right hand limit, into limit as x approach, is that better arrow?
There you go.
To negative 1 from the left side, f of x. And limit as x approaches to negative 1 from the right side, f of x. You can write out the whole function here, by the way. You don't have to write f of x. I just do it because it's faster. So, Ananya here is going to go over how to do this problem using your guys' method. And then I will show you a different method, which I find to be much simpler, but it also requires a little bit more intuitive thinking.
We're not very good at that. Okay, so we have negative 1 in the middle as your, a value or what your limit is approaching. And then your two closest integers.
You should use different colors, like Sol Concord.
Alright guys, I'm going to pull out the red here. The red, that it says red. Okay, so basically we got to test values in between. Then my left hand side and then my right hand side. Let's take negative 1.5, because we're really creative here. Negative 1.5 over negative 1.5 plus 1, which is negative 1.5 over negative 0.5, which equals 1.5 over 0.5. And I have no idea what that is, but it's something more than 1. So, it's going to go in this direction. Let's do the same thing with a value between negative 1 and 0. 0.5. That's 0.5 over 0.5 plus 1. And that's 0.5 over 1.5. And in the previous recording, Aditi told me that that equals 1/3, which is also in this direction. Which means that there's no value that the left-hand side and the right-hand side are converging to.
Oh, like they agree on?
Yeah, that they agree on. So, because they don't agree, we say that it doesn't exist. And that is what we do for pre-calc honors, but I think in BC you have to actually solve for, like, is it infinity? Is it negative infinity?
Yeah, so it does not exist means it is not a continuous function. Make sure to write that out instead of just saying does not exist on your test.
It's not a continuous
So then you say, I don't know, therefore not continuous. You probably do like a full sentence, like f of x, but I'm not going to do that. So now, I will show you how we would do it in BC. And I don't think you guys are really going to need to use this method, but I personally think it's a lot easier to understand than the pre-calc method. So I will show it to you in case it helps you. So we have a function, I'm not going to graph this, but it goes like at negative 1, right? And we need to find it, it goes to negative 1. So first, we'll take the left-hand side. So basically, that's as x approaches negative 1 from the left side, it's going to get closer and closer and closer and closer and closer to negative 1. But it's never going to reach there because negative 1 doesn't exist. So therefore, we take a point that's really, really close to negative 1, but doesn't actually exist. Like negative 1.0000001. And if you're wondering why I didn't do negative 0.0000999999999, it's because that would be on this side of negative 1, and we're doing on this side right now. So, if I have, shut up, Ananya. Shut up,
what you
Ananya.
did in the last recording.
Listen, I was a little bit on autopilot. I plead the fifth. Anyways, so you don't actually have to write out this number. It's just like a way of thinking intuitively. So if I have like a number like that, right? That's really close but not quite negative 1, and I plug that into my function, that's going to be like 1. I don't need to add that. And so that is like equals to some negative. And then you told me to use like hashtags in the last recording for numbers, so I'm going to do that. Over, and this is like negative 0.0 is like a really like negative 1 minus a really small decimal plus 1, so that's just going to be that really small decimal left. So that's going to be, and it's going to be negative. So it's going to be some number over some like really small number. And these negatives cancel out, so that's just infinity, right? Because if I have like, I don't know, 3,000 over 0.000001, that's a really big number. And as this number, this denominator number keeps getting smaller, this denominator number keeps getting smaller, this whole total is just going to increase. So by that logic, we know that this whole thing approaches infinity. Now, if I do it from the right-hand side, it's going to approach negative 1 from the right-hand side. So it's going to get really close to negative 1, but it's never quite going to get there. So for that, I can do negative 0.9999999. You get the idea. And that's going to be negative 0.9999999, etc., plus 1. And so that's going to be that negative number over, this time the decimal is going to be positive since 1 is bigger than 0.99999, but it's still going to be a really small number. So it also approaches infinity. But remember, since we have that negative, this is going to approach negative infinity. And so as you can see, negative infinity is not equal to infinity. So therefore, left-hand side, well, this isn't the left-hand side, but right-hand limit is not equal to the left-hand limit, so therefore the function is not continuous on x equals -1. Okay, I also wanted to go over an example of like the thing I was talking about earlier with removable discontinuities, but I can't think of one off the top of my head, so we're gonna do like a really lazy way out. So let's say f of x is a piecewise. I hate piecewises. They're gonna show up a lot when you do continuity. It's kind of a problem.
The piecewise thing was the one, like, you were supposed to make a piecewise function for that right-hand, left-hand side limits thing on that test. I didn't do that.
Alright, so anyways, let's say I have x squared, provided x is less than 0. Now, it's 3 when x equals 0. And then it's x squared again when x is greater than 0. So that's... Why are you laughing, Ananya? So that's just gonna be like this, right? So we can easily see that it's discontinuous here. But if you were to go through the math process of it all, if you take the limit of just like this side and this side, because you think it's like left hand and right side, sorry, left hand and right hand, then they're gonna equal the same thing, pretty much, right? They're gonna go to the same place. They're both gonna go to, they're supposed to go to 0. I drew this graph wrong, but pretend I didn't. They're both gonna go to 0. So you think that the limit exists, or it's continuous. But it's not continuous, because like right here, it's 3, so it's a removable discontinuity. So you have to make sure to take the limit in a piecewise of all of the different parts, right? So then if I do like limit as x approaches to 0 of 3, that's just going to be 3. So even though my limit over here was 0, and my limit over here was also 0, my limit over here is 3, so it doesn't all match. So therefore, it's not continuous. Anything else you should like go over?
This is about continuity, right?
Yeah, but I can do like, I mean, I prefer to keep it related to continuity, but
Then you're